Day 58 notes, Advanced Algebra 2. Today we begin a new unit. This unit will cover polynomials. During the last two units, however, we've been working with special polynomials known as quadratics. Now, a quadratic polynomial is one that takes the form ax squared plus bx plus c. You'll remember that a, b, and c were numbers, and we always dealt in the same form with an x squared, an x by itself, and then this number that had no x values with it. If we take a mathematical approach to the definition of a polynomial, it'll look very similar. The description or definition of a polynomial will follow this pattern. And if this is the first time you've seen this subscript notation, it might be a bit confusing to you at first. We would say that a sub n, or a subscript n, times x to the nth power, plus a sub n minus 1, or a subscript n minus 1, times x to the n minus 1 power, plus this triple dot means that we're going to continue the pattern. So the next one would have been a sub n minus 2 times x to the n minus 2, so on and so forth, till we get down to the end here. A sub 2 times x squared plus a sub 1 times x plus a sub 0. Now, this is the definition. This is the description that we use to generalize the form. N can be any whole number imaginable. We could have n equaling 3, or 4, or 5. It could be as large as 10, or 1,000, or 1,000,000 if we really wanted to. But we would continue the process in counting down the size of n until we get down to 0. If you look carefully, this description at the very end really represents a quadratic equation. Instead of using a, b, and c as different letters here, we're calling this a2, a sub 2, a sub 1, and a sub 0. We would run out of letters to use if we had a polynomial larger than 26, right? If I called this a, b, c, d, all the way down to z, we'd have room for 26 terms in the polynomial. But sometimes polynomials can get larger than that. So that's why mathematicians have gone to this notation, where they reuse the letter a to represent any coefficient, and they're going to assign a number to go along with that coefficient, and that number will decrease as the polynomial is read. Now, describing a polynomial in an algebraic sense is fine, especially if you can understand the techniques here. But what we're going to see eventually, and later in this video, is that polynomials, when graphed, are what we would call smooth and continuous. And we're going to describe that in just a little bit. But first things first, let's decide whether or not the following examples are polynomials or not. Remember, a polynomial has to follow this form where a and a sub n represents some number. So it can be a whole number, it could be a decimal, a fraction. When we're talking about a sub n minus 1, a sub 2, a sub 1, and a sub 0. Those are allowed to be any sort of number. The only restriction here is that the letter n itself, so this n value and these exponents, must be whole numbers. Those are not allowed to be fractions or decimals. So, considering that, let's go take a look at some of these examples. Try to decide whether or not a through f are polynomials. I'm going to pause the recording, and I encourage you to try these on your own. Check your answers with mine in just a moment. And here we go with the solutions. Option A, yes, this is a polynomial. We have coefficients, a constant term, and an exponent that is positive and no decimals. That's a whole number. Same thing occurs down here in part B. Yes, this is a polynomial. The coefficients are allowed to be fractions, so if you saw this and thought that that was a problem, since this is a number in front of x, we're allowed to use it there as a fraction, so that's not a problem. All powers here are whole numbers as well, so yes, that is a polynomial. Option C, yes, this is a polynomial. All of our coefficients are numbers. Those are allowed to be fractions if they came out to be, but they are not in this case. And when we look at the exponents here, these exponents where the n value was, that must be a whole number, and all of these are. Looking at option D, this appears to be a polynomial. Everything seems to work until you get to this last exponent. This exponent is a value of -4, and -4 is not a whole number, so therefore this is not a polynomial. You might think that -4 is a whole number, but remember, whole numbers are all the numbers that start at 0 and work their way up from there. So they must be positive with no decimals. So do not include a number like -4. It is not a whole number. Hopefully you recognized option E as not a polynomial, again because of the last exponent. This is a fraction, and fractions are not whole numbers. That's the value that prevents this from being a polynomial. Option F is a polynomial. None of our coefficients violate any of our terms, and also the exponents, they are all okay too. They are all whole numbers. So yes, letter F is a polynomial. If I took any of these examples, A through F, I could type them into an input function on the TI Inspire calculator, and it would return a picture of a graph for us. Now, if we exclude D and E, since they are not polynomials, and look only at those that are left, then the graphs that are displayed on the calculator would be called continuous and smooth. So we know that polynomials are continuous. That's what we mentioned just a few moments ago. And what that really means is that the graphs do not have any breaks or jumps within them. So a continuous essentially means that if you had a pen on your paper or a pencil on your paper, you can draw from left to right without lifting your pencil from the paper. So here's an example. This graph on the left is continuous because if I started here in this window and wanted to recreate the rest of this drawing, I could continue to draw this entire shape without lifting my pen. However, this graph here on the right is what we would call discontinuous because I cannot draw this shape without lifting my pen from the page. Notice to draw these parts, I have to lift my pen to continue drawing them. And even if I zoomed out and looked at this as at a wider picture, this graph here on the left again could be drawn without lifting my pencil. So the graph might be doing some other strange curves over here on the left, but it would always meet up here, continue this pattern, and it would go off to the right, and it could make some strange shape there as well, and it would be continuous over the entire domain. There's no spot that I'd have to lift my pencil whatsoever. On these discontinuous graphs, however, even if you have to lift your pencil once, that would be a cause for a description called discontinuous. So with that in mind, let's take a look at these graphs and decide whether or not they model polynomial equations. So first choice, second, and third. Does this first example make a polynomial? Or does the graph represent a polynomial function, I guess is a better way of asking that. And here we would say yes, because the graph is continuous. Does this graph represent a polynomial? Here the answer would be no. It's a discontinuous graph because in order to draw this, I have to lift my pencil right here at this point. So no, that's not a continuous graph. What about this example here? Is this continuous? Yes, it is. So therefore, it would model a polynomial. Now, we can have continuous polynomials, we can have continuous graphs that are not polynomials. Each of these graphs, each of these four examples are continuous. I can draw each of them without lifting my pencil. But if I tell you that a polynomial must be smooth, then that should tell you that at least one of these pictures is not a graph of a polynomial. So I'd like to pause this video here, and I'm going to ask that you do the same. Try to find the one graph in this group that is not a polynomial. Keep in mind, polynomials must be smooth. So use that to decide which one is not a polynomial. If you selected this choice as not a polynomial, then you would be correct. This is a polynomial, this one's a polynomial, and this one's a polynomial, but this one is not a polynomial. And so the idea here is that for a smooth polynomial to exist, it has to be continuous and it can't have any angles to it. Now, this is a graph of an absolute value equation, and it is continuous. I can draw it without lifting my pencil. But this point down here at the bottom is an angle, or a sharp angle, that prevents this graph from being what we would call smooth. So again, this picture here is an example of a continuous graph, but it is not a polynomial because it has a sharp corner to it. And that about does it for our introduction to polynomials. So be sure that you include all of this information into your notebook for today. We started with a definition of a polynomial. We then moved on to some examples of polynomials. We discussed how polynomials must be continuous. We practiced a little bit with them, and then we went on to say that polynomials must also be smooth, continuous and smooth. And so we looked at a couple examples of smooth polynomials and those that are not. So be sure that you understand the information that was presented in this video, and we'll use that for our activity tomorrow.